In this video, I'm going to go over 5 homework problems on spherical coordinates. Now, I've done 6, 8, 18, and 27 in detail in a handout to you, so this will just be on the other problems here. Problem 12. You're given a table of certain values for x, z, and theta are given, and you want to find the other values here, y, r, rho, and phi. So we're converting from, well, not really between any two systems. We have some of the coordinates from these different systems, and we're trying to find the other. So, what should we begin with? Any idea? Just let me know what you think we should begin with. R? Okay, so let's begin with R. So why would R be a good thing to use, to go for here first here is we have x and we have theta, and we know that x equals r cosine of theta. So we can get R fairly easily just by using that information. So in fact, this is it. We have x is equal to r cosine of theta. I'm plugging in what we know. We know x is 3, and we know that theta is 11 pi over 6. So we have this, and then cosine 11 pi over 6 is the square root of 3 over 2. You can divide by the square root of 3 here. You'll have square root of 3 on this side then, and then multiply by 2. And r will be 2 root 3. So that gives us r. Now, what should we go for next? Any thoughts on that? Y? Well, that sounds good. So let's go figure out what y is. Y we can do now because we have y equals r sine theta, and we know what r and theta are. So y equals r sine theta. R we just calculated was 2 root 3, and theta is still 11 pi over 6. So we just want to take 2 root 3 and multiply it by the sine of 11 pi over 6. This is going to be minus 1/2 here. So when I multiply it by 2, I get minus 1 times the square root of 3. So y is minus root 3. Now what should we do? Any thoughts on that? Rho? Okay, let's do rho. So what do we know about rho? Well, rho is you take the x, you square it, you take the y, you square it, you take the z, you square it, you add those up, and then you take the square root. So we're going to have 9 plus 3 plus 36, and then we want to take the square root of that. So that's 12 plus 36, that's 48, and so we have the square root of 48. Now 48 is 3 times 16, so we can take a 4 out of there. 16 is 4 squared, and so I'm going to write this as 4 root 3. Now what do you think we should do? We'll solve for phi. Okay. So let's do that. So for phi, again, what we always really want to use for this is that the z is equal to rho times the cosine of phi. So z we know is minus 6. Rho we know is 4 root 3. And so we're just going to figure out phi from here. So this is 3 times 2 if you want. You divide by square root of 3, then you'll have the square root of 3 times 2. Divide by 4. And 2 will cancel, and you'll have minus root 3 over 2. So cosine of phi is minus the square root of 3 over 2. So what does that make phi? Keep in mind, phi is between 0 and pi, and phi is going to be 5 pi over 6 then. So this completes the table for us. Now we know all the variables x, y, z, r, theta, rho, and phi. So this finishes this problem. The next problem we want to do is we want to express the volume of G in spherical coordinates. So we don't want to evaluate the actual volume, but we want to write it in spherical coordinates. And what is G? Well, we're inside a cone here, and that's going to be the side here, this cone. We're inside that cone, and we're between two spheres, one of radius 2 and one of radius 3. So the inside one has radius 2, and the outside one has radius 3. Now this is going to go completely around the z-axis. The z-axis is going straight in the middle here, coming out here. And because it's going completely around the z-axis, theta is going to go from 0 to 2 pi. Rho, you can tell, is going to go between these two spheres. So the big question here is what's phi? And whenever we have something like this, and we want to write it, what phi is, this should be phi equals something because it's a cone. And the way we solve that is the following. First, I replace the x squared plus y squared with r squared. The square root of r squared is r, so I'm going to have r over root 3. So this cone, again, is r over root 3 is equal to z. Okay, now we write z and rho in spherical coordinates. Z is rho cosine of phi, r is rho sine phi. So we just do that substitution, and we can cancel the rho from both sides. And the tangent of phi is going to be square root of 3. So I divided by cosine of phi and divided by rho and multiplied by the square root of 3. So we have tangent of phi is equal to the square root of 3. And what does that mean about phi? That means that phi is going to be pi thirds. So that tells us the cone is where phi equals pi thirds. So you're going to be starting at the z-axis where z is 0, and phi is going to go all the way to that value of phi equals pi thirds. So let's remember what we just said. We want theta to go from 0 to 2 pi all the way around the z-axis. We want phi to go from 0 to this cone, which is phi equals pi thirds. And we want rho to go from 2 to 3 between these two spheres. And then we're doing volume, so the dv should be rho squared sine phi d rho d phi d theta. So again, theta goes from 0 to 2 pi. Phi goes from 0 to the pi thirds we computed. And rho goes from 2 to 3. And again, we're integrating rho squared sine phi d rho d phi d theta. That's just the dv. So we have 1 dv. We're getting volume. So that's the answer to that question. And let's go on to the next one. Here we want to use spherical coordinates to find the volume of the solid that's bounded above by the sphere, rho equals 3, and below by the cone, phi equals pi 6. So the basic shape of this is an ice cream cone. You have the cone on the bottom and the sphere on top. So we're going to have theta going all the way around the z-axis again, from 0 to 2 pi. Phi is going to go from the z-axis to pi 6. And rho is going to go from the origin to rho equals 3. And this is a volume, so the dv is rho squared sine phi d rho d phi d theta. So again, theta goes all the way around the z-axis. Phi goes from the positive z-axis to phi equals pi 6. And rho is going from the origin 0 to 3. And this is dv. So we want to evaluate this because here it is asking for us to find the actual volume of this solid. I integrate the rho squared first because I have d rho here and treat sine phi like it's a constant. I just put it out here. But we're just getting rho cubed over 3 evaluated from rho equals 0 to rho equals 3. Of course, here it's 0. When you plug in the 3, you can cancel a 3. It's just going to be 9. So we're integrating 9 sine phi. And the sine phi is going to give us a minus cosine of phi when we integrate. And then we want to evaluate that minus cosine of phi from phi equals 0 to pi 6. At pi 6, we're going to have minus the square root of 3 over 2. And at 0, we're going to have minus 1, but we're subtracting that, so that'll make it a plus 1. So we're going to end up with 1 minus the square root of 3 over 2 times the 9 here. So I went ahead and multiplied the 9 times 1 and the 9 times minus the square root of 3 over 2. And this is a number now. We want to integrate this, and we're just going to get this number times theta, where theta is going from 0 to 2 pi. So we're just going to get 2 pi times this number. That gives us 18 pi for 9 times 2 pi. And then when I multiply by 2 pi, the 2 will go away here, and I'll have 9 pi squared root of 3. So let's go to the next problem. The next problem is a triple integral that's given in terms of x, y, and z, and we want to rewrite it as a triple integral in spherical coordinates. So we just want to write down a triple integral for our answer, but it should be in spherical coordinates. So I went ahead and replaced z with rho cosine of phi. Rho squared for x squared plus y squared plus z squared to the 3 halves will be rho cubed. Again, rho squared to the 3 halves is rho cubed. And then dz dy dx is dv, and that gets replaced with rho squared sine phi d rho d phi d theta. So we're going to have a rho to the 6 cosine phi and sine phi here, d rho d phi d theta. And what about the limits of integration on theta, phi, and rho here? Well, what is this a picture of? Let's see, we have x going from -1 to 1, and we're going to look in the xy plane, and we're going to have y going from 0, the x-axis, up to the square root of 1 minus x squared. And you should recognize that in a circle, it's just going to be x squared plus y squared equals 1 if I set this equal to y. So we're going to have y going from 0, the x-axis, to this circle of radius 1 centered at the origin. So in the xy plane, we have this half circle that's above the x-axis. And for z, we want z to go from 0, which is the xy plane, and go up until it hits this sphere. This will be z squared equals 1 minus x squared minus y squared. So that's just x squared plus y squared plus z squared equals 1. And z is positive because it's the square root here. So we're just going to the top part of the sphere. So z is going from the xy plane to the sphere. So this looks like 1/4 of a sphere. You have in the xy plane a half circle, and then you're going from there up to the sphere. Well, if we look in the xy plane, this half circle, we can see that theta is going from 0 to pi. Again, it was just this half circle that's above the x-axis. So theta is going to go from 0 to pi. So theta is going from 0 to pi, so what about phi here? Well, remember, we're just doing the part of the sphere that's above the xy plane, where z equals 0, and going to the top part here. So if you start at the z-axis, where you're touching this part of the sphere, the phi goes all the way down to the xy plane, where phi is always pi halves. You don't go beyond the xy plane because we're starting at the xy plane where z equals 0. So phi is going from 0 to pi halves. And then rho is just going to go from the origin to the sphere, and the sphere was of radius 1. So rho will go from 0 to 1. So theta again goes from 0 to pi, from the positive x-axis to the negative x-axis in the xy plane. And phi again goes from 0 to pi halves. And again, that's coming from the fact that this quarter of a sphere we're looking at has its bottom on the xy plane, and then it comes up to the z-axis. So you're starting at the z-axis with phi and going down to the xy plane. Rho is going from 0 to 1. 1 was the radius of the sphere. So again, we can combine these and simplify that. Rho to the 6 cosine phi sine phi if we want. But other than that, we're done setting this up, and this will be the answer to this problem. The last problem, number 29, that we're going to do is similar. We want to rewrite this one in terms of spherical coordinates. So the integrand, rho squared to the 3 halves, will give us rho cubed. And the dx, dy, dz will be giving us a rho squared sine phi d rho d phi d theta. But we need to figure out the limits of integration. So let me get started here. Again, I'll put that rho to the 5th. sine phi d rho d phi d theta. And we want to figure out what's going on with theta, phi, and rho here. So we're going to look at this picture. This picture's really a little bit nicer than what we had in the previous problem. And so this is just going to be a quarter of a circle in the yz plane where y and z are positive. The circle has radius 3 centered at the origin. And then we want to go from that quarter of the circle in the yz plane where x equals 0 is the yz plane, to the sphere of radius 3. Again, this would just be x squared plus y squared plus z squared equals 9, so it's just a sphere of radius 3. So we're going from the yz plane, that quarter of a circle, to this sphere, and we're just going to have then an eighth of a sphere, the part that's in the first octant, of a sphere of radius 3 centered at the origin. So theta is just going to go from 0 to pi halves. In the xy plane, we just have a quarter of a circle in the first quadrant, so it's just going to go from 0 to pi halves. Phi is going from the positive z-axis to the xy plane, so that's again 0 to pi halves. And rho is just going from the origin to the radius of the sphere, 3, so rho is going from 0 to 3. And that'll be the setup for this problem. And that finishes this problem and finishes this lecture.